Just recap where we are. We're 1 week away from our first midterm. That's one thing it is, next Friday. Just so you kind of know where, what the coverage will be on that. It'll be the first 4 chapters of our book, okay, which pretty much ends with today's lecture. The chapter 5 on conduction will be lumped with the second midterm, just so you know what's happening there. And we'll talk more about the first midterm next week and review on Wednesday. You turn the homework in. I'll get that back on Monday, and we'll go over the homework. I'll pass out some practice midterms with solutions that I've asked on previous exams. So you'll see what kind of problems are on the midterm. I'll pass those out on Monday. Okay, so as we said, we're in chapter 4. We'll finish chapter 4 on Monday. But where we left off last time, we were looking at heat flux plots in conduction heat transfer. What is a heat flux plot? A heat flux plot is a graphical diagram of the heat flow lines called adiabats and the constant temperature lines called isotherms. And there's several rules you follow when you construct them. We went over those, and we'll do one more today. So that's where we left off last time. When we started chapter 4, we said these two-dimensional conduction problems can be solved by one of 3 methods. Analytically, and we showed you one simple solution for a rectangular plate, and the solution was an infinite series. It was pretty long, complex solution. And we said we're not going to do much more on the solutions analytically, but we'll look a little bit at numerically and graphically. So, okay, we covered the graphical part, the flux plot. Today we're going to start to cover the numerical part, but I'm going to back up a bit because there are some results from analytical solutions that are available to be used. Table 4.1 in chapter 4 lists, I think there is 12 cases. 12 cases of problems that have been solved analytically. The solutions have been expressed in something called a shape factor. And let me put down the equation you would use to get Q. The equation you use to get Q is this. So let's just go through an example. I'll explain how to use it. The first case in table 4.1 is a sphere of diameter d buried beneath a surface kept at temperature T2. The sphere surface temperature is T1. The sphere diameter is d. It's buried from this surface down to its center, a distance z, in a material of conductivity K. For instance, you bury the sphere in soil. Okay, so here's a sphere buried in soil. The sphere temperature is 100 degrees C. The top of the soil temperature, 30 degrees C. Okay, you go to this table. You get, for your geometry, you get your shape factor, S, capital S. You put it up here, multiply it by K out of the material, I don't know, soil, concrete, whatever it might be, times the temperature difference. You've got Q. It's that simple and straightforward. All the work's been done, of course, in getting the shape factor from analysis. And then the last column are some restrictions you have to apply to use that shape factor. In this case, it says, just make sure that the sphere is buried below the surface of the soil. Don't look at a case like this, where here's the top of the ground and there's a sphere. Nope. It's got to be totally buried in that material of conductivity K. And there's another one given there. 2 cylinders of infinite length. D1 comes out of the blackboard. Cylinder, typically pipes or tubes. D2, cylinder, comes out of the blackboard. Different temperatures, T1 and T2. Center line separated by a distance W. The conductivity of the material between the two is K. Here's the shape factor S. You can only use this for very long cylinders. The length must be much, much greater than D1 or D2. The length must be much, much greater than W, the spacing of the 2 cylinders. So they give you some restrictions to use. And we'll use those in an example in just a minute. Yes?
Did you assume that there's infinite soil?
Yeah, oh yeah. Thank you. Let me read it. Yeah, I'm glad you mentioned that. Here's what the table says, because I left some words out. Okay. Cylindrical conduction between 2 cylinders of length L in an infinite media. An infinite media. So what he means is these are buried so deep you can forget about that surface up here. Okay. So how far is it up this way? Infinite. To the left, infinite. To the bottom, infinite. To the right, infinite, or approximately so. Approximately so. Yeah. This case here, it's not buried in infinite media. It stops here. Okay. If these 2 are buried in soil, where's the top of the soil? I don't know, but it's a long way up. That's the point being there, okay?
So not all of the heat that's coming out of the pipe goes into the surface, right? Some of it
Which one now?
The top one.
Right. All the heat comes out of the pipe, goes to the surface, yes.
Doesn't some of it just dissipate into the soil?
Oh, yeah. Uh-huh. Yeah. Okay, since you ask, I'll show you. I'm going to draw a flux plot. Let's make it a cylinder, make it easy. It's a cylinder. Where do you think heat goes? I think right there first. This is hot, that's cold. Straight up, of course. Don't forget the rules. You get my point? I'll take one more just for you. It goes down 50 feet down. I can't draw down there. It comes back up here, and it goes out up here. Every line that starts from that cylinder is going to end up on the top of the soil. But it might, how much goes that way? Oh, not much, because look how long that line is. And what's the resistance? The longer you have the heat go, the bigger resistance. This line, tremendous resistance. Very little heat flows here. This line here, oh, a lot of heat flows there. A small distance, okay, small resistance, bam, heat goes up. So, yeah, it goes down. There's a line. Say, well, how about this guy? I don't know. He goes to Southeast Asia somewhere, straight through the earth, and then comes up again to the soil. I don't know where. But, that's the game we play. It works that way. So that's the flux plot. But, yeah, good question. Okay, so what we do, if we get a problem, here's our problem. We look at the geometry, obviously, and we say, okay, what do we have here? We have soil, 2 pipelines buried in soil in an infinite media. Okay, no surface of the soil. They're buried deep. And somebody said, well, what's buried deep? The first class this morning. And he said, what does that mean? Well, let me tell you what this means, first of all. If z is 1.01 and d over 2 is 1.0, it's okay. It's okay. This guy here, if L is 1.01 and d1 is 1, oh no, ain't gonna work. This is called greater than. This is called much greater than. You're the engineer. You have to make that call. Nobody's going to tell you. You make the call. Do I think 10 meters long, 1 meter diameter? Is that okay? Probably. Is 100 meters long, 1 meter diameter? Oh yeah, 100 to 1. That's very, very much larger. So, but in the world of the classroom, the textbook, and exams, here's the rule. Look for key words. If you see words like long pipelines, oh, okay, that means I think I can use that equation. Long means much long. We had that in chapter 1. We said in radiation, if you've got a small object in a large room, you can use this equation for radiation. You put a dime on the surface of the table at 500 degrees C, and these room walls are 30 degrees C. This is definitely a small object in a large room. So, but what's the magic number I use? No, there's no magic number. You make a call, okay? So, look for keywords. Look for, in radiation, look for small object in a large room. Problem like this, look for long pipelines. If you see those keywords, they're giving you hints of what to do in table 4.1. Okay, so here we are. These are parallel pipelines, very long, okay. Diameters given, they're buried in soil. K, soil's given. Diameters given, temperatures given, find Q prime. Since I don't know how long the pipelines are, I'm going to find my answer in terms of watts per meter. Watts per meter. Okay, so that's Q prime. Now, let's go back and practice one more time. Flux plots. I'm going to take an example of 2 cylinders. I'm going to make life easy and have them both the same diameter, but you can do it for different diameters. I'm going to space them apart a little bit more, I think. Out here, maybe, yeah, okay. Okay, same diameter. T1, D1, T2, D2. Material has a K value, whatever it is. This could be 2 buried pipelines. Well, it is 2 buried pipelines. Sometimes in large fields of like petrochemical industry or maybe solar fields, they have to have trucks to come out to clean the collectors, or trucks for maintenance, and trucks going where pipes don't do good things. So sometimes you want to bury the pipes under the roadways or something, whatever it might be. But a reason to bury the pipes, so you dig a trench, I don't know how big, 3-4 feet, so deep, and you bury the pipes in there and then backfill with sand and soil. So that happens in the real world. This first case over here, this happens in the real world. You bury something that's hot, I don't know, maybe it's nuclear waste, I don't know. And you want to know, how long it's going to, what the temperature is with time as it cools off. Okay. So anyway, those are all practical geometries over there. That's what I'm saying. That every geometry means something to engineers who are working in this area. Okay, back to this. We're going to draw a flux plot. Okay. First of all, is there symmetry? Don't forget rule 1, flux plot. Look for lines of both geometric and thermal symmetry. Try that guy. No. That guy. No. This guy. T1, flip it over. T2, no. Try this guy. T1, T1, T2, T2. Yep, here's one right here. That line has symmetry, both geometric and thermal symmetry, which of course, obviously is common sense. You know heat's going to go from the hot to the cold straight across. Why not? Rule 2, lines of both geometric and thermal symmetry are automatically adiabats. Let me go back and tell you where the word adiabat comes from. Here's my flux plot. This is an adiabat. This is an adiabat. Heat comes in here, Heat goes out here. If 100 watts comes in here, 100 watts goes out there between those two adiabats. Well, what does that mean then? That means no heat crosses that line, those two lines. If 100 watts comes in, 100 watts goes out, no heat crosses those lines. What's the definition of an adiabatic wall? It's a surface where no heat crosses. Okay, that's why. Because no heat is going to go out that way. Illegal, cannot do. That's why the lines are called adiabats. Okay, so here's our first adiabat. Now I think it's one of the rules, I forget, 3 or 4. When an adiabat intersects an isothermal boundary, it does so at right angles. Okay, right angle, right angle, right angle, right angle, and so on, and so on. And so on. And so on. There they are. Those are the heat flow lines. Let's label them. Okay, next step. Draw the isotherms. Okay, here's the rule. Adiabats and isotherms cross at right angles everywhere inside the boundary. Okay. If it helps you, play this game. T1's 100. T2 is 0. T1 is a circle at 100. T2 is a circle at 0 degrees C. Where do you think the line 90 degrees C is going to be? Here's 100. Oh, I think it's going to be really close. Good, good estimate, right. Okay, so there is the 90-degree line. The T2 is 0 degrees. It's a circle. Where do you think the line 10 degrees is going to be? You know, I think it's going to be really close like this. Yep, you got it. Now here's the rule. Everywhere they cross inside, they must cross at a right angle. As best you can draw. Okay. Continue. I'm not gonna. Everywhere they must cross at a right angle. I'll draw one more. Right angle to the best you can draw. Okay, and these guys are the isotherms. Okay, so just for an engineering intuitive feel of the problem, that's what it looks like. That's where the heat flows, that's where the constant temperature lines are. It gives you that feeling. You're not just solving a problem mathematically, but you get that engineering intuitive feel for the problem. Okay, back over here. That wasn't what we're supposed to do. We're supposed to find Q prime. Okay, got it. We go over here to table 4.1. We say, okay, it's case, whatever it is. I think it's case 4. There it is, S equal 2 pi L. Let's write down our Q equation first. I don't want Q. I want Q prime. Q prime equal Q over L. Okay. Let's put S in here. 2 pi L. Gosh, minus 1. I'm not going to put all that in there. You can see over there what it is. This should be equal. What am I doing here? S K, soil, back of the book appendix. T1 given 175, T2 given 5. Cancel, cancel. The L's cancel out, of course. Put the numbers in there, and we get for Q prime 110 watts per meter. Now, you can also, if you look at this equation for Q up here in terms of S, you can also recall in chapter 3, we had that, conduction resistance, okay? T1 minus T2 divided by R. R is a conduction resistance. So, in our case then, R, look at these two equations, 1 over SK. So I'm going to work just over here now with the resistance model. R is equal to 1 over SK. Okay. If I want Q prime, so, okay, my resistance there then comes out to be 1.55. Let me just make a note here. Okay, that's S prime. See, we can't use R because we don't know how long it is. So we have to base everything on per meter length. So we have to use the R primes because he asked me to find Q prime. He didn't say find Q, he said find Q prime. So we have to base everything on per meter length, okay? So that's, this guy right here is S prime, just so you know what it is. 1.55, okay? It's got the K in it from there. The K is lumped in there too. There's a K there. So there's a K, S prime. There it is right there, okay. Now, let's go back to chapter 3, our resistance model. R prime, T1, T2, Q prime. There it is. So Q prime is equal to T1 minus T2 divided by R prime. Of course, you get the same answer either way, 110, 110. So you can use the resistor model, though, if it's helpful. When is it helpful? Well, maybe a problem involves convection on a surface. Is there a resistance for convection? Oh yeah, 1 over HA. So this resistance model might be very useful on problems where there's convection on a surface in this 2D heat transfer. So that's when you might use that particular resistance, okay. Okay, any questions on that then? All right, you have 2 problems for homework out of table 4.1. You pick out the right geometry, you get the shape factor, maybe you need the convection resistance. If so, use the conduction resistance, here's the conduction resistance, to solve the problem. Okay, anything else on that before you go on then? Okay, so that takes care of the first 2 of the 3 ways to do 2D problems. We looked at the analytical solutions. We used some simple geometries that we have available based on the analytical solution. We looked at the flux plot, and from the flux plot, we could get an estimate of Q. We can get an estimate of the temperatures in a 2D body. But now we get to number 3. Number 3 is looking at numerical methods. Okay, so let's take a look at how we analyze a conduction problem, a 2D conduction problem, by numerical methods. So we have some homogeneous body. And it looks like this, maybe. Okay, conductivity. It's a conduction problem. And we're going to solve this by a numerical technique. To start that, we draw for the object a grid. Now, the grid, I'll just draw one here. No longer is the body homogeneous. Now we're assuming that the mass is lumped at these nodal points. So here's the nodal points. So these are nodal points. Every node has a temperature. The nodes exchange energy with their neighbors through what we call heat conducting rods. So this is a heat conducting rod. So we replace the homogeneous material with the grid, and at the nodal points, that's the temperatures in the body, and these different temperatures are connected to each other by heat conducting rods. The only way heat's conducted then is through these heat conducting rods. So it's an approximation, obviously. We'll see later on how good it is. Now, we're going to look at this guy here. Take one node out of here, okay? So take one node out. That center node right there. We're going to call that center node Mn. M the column, N the row. And then there's 4, how many adjacent nodes are connected to that center node? There's 4 of them, directly connected by heat conducting rods. So let's get the numbering system right on these guys. Okay, he's M minus 1N. He's M plus 1N. Mn minus 1. Mn plus 1. So The node Mn replaces the material in the dashed lines. Mn is called the center node. And by the way, when you set your grid up, this is delta x and this is delta y. So over here, delta x and delta y. This is delta x. And this is delta y. Now, one way, there's a couple ways to solve this. We're going to do an energy balance on the center node. So energy balance on the center node. And we say the sum of all the Q's coming into that node equals 0. Now don't forget, it's just conduction. This is a conduction problem. So we're saying that the conduction that comes in from the adjacent nodes into the center node must be 0. And we know conduction Chapter 1, we use that equation. Fourier's law, the simplified version. And you say, yeah, but if I have 5 watts come in here, 5 watts here, 10 watts come in here, 10 watts come in here, that's 5 plus 5 plus 10 plus 10. That's 30 watts, and 30's not equal to 0. No, don't worry about it. Do you know which way the heat flows when you start? No. So then what are you going to do if you don't know which way the heat flows? I'm going to make life easy. I'm going to assume that they all go in equal to 0. When I'm done, I might find out some were going out and some are coming in. But my math will take care of that. So you don't worry about that. The math will take care of itself because I know they all can't come in. Okay. If you don't know in that problem which way the currents are, I'll tell you what most people do. Most people, when they write the equations, they say I1, I2, I3. But notice what most people do. They assume they're all clockwise. Are they? Of course they're not. Then why assume they're all clockwise? Because I don't know which way they go. I'll take the easy way out, and I'll find out that this one might be the wrong way. He's going that way, or whatever. The math takes care of itself. So whether it's DC circuit theory or whether it's heat transfer, the same rule applies. If you don't know which way the heat goes, assume the sum of all the Q's into the node, 0, and later on, your math will tell you if you're right or wrong. Okay, let's start from him. Take him, Q m minus 1n, going to node Mn plus Q m plus 1n going into node Mn plus Q Mn minus 1 going into node Mn plus Q m n plus 1 going into node Mn equal 0. Okay. Now use Fourier's law to get those Q's. All right, m minus 1n. So here it is. K times A. Okay. K times A. All right, let's see what area. From the left-hand node to the center node, here's the area, my hand. What is that area? Delta Y high times 1 into the board. The area is delta Y high times 1. That's the area. Ka divided by L. What is L? L is the length that the heat was transferred over. Okay, left-hand node, center node. What's that length? Delta X times the temperature difference, T M minus 1N going to T M N. Okay. Let's take the right-hand node. Right-hand node to center node, T, M plus 1N. Well, let's do the first thing first. K times the area, delta Y times 1 divided by the length traveled, delta X, times the temperature difference, M plus 1N minus T, M, N. Got it. Let's take from the bottom node to the center node. Okay, K. Okay, the area changes now. The area for the bottom node to the center node is where my hand is. The area of my hand is delta X times 1. Divided by the length over which the heat's transferred. That distance right there, delta Y. Plus, T M N minus 1 minus T M N plus the last one from the top node to the center node, K, the area delta X times 1 divided by delta Y times the temperature difference equal 0. Okay. Now, I say, you know what? There's a K in every term there. There's a K every term. I'm going to divide through the whole equation by K. Good idea. Gone, 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 gone. Divide through by K. Now I make a simplification. I say, you know what? If I make the grid a square grid, delta X, delta Y, cancel, 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 makes life a lot easier. Conclusion, here's my equation. So that is the first equation we've got for our finite difference analysis. It's the finite difference equation for an interior node. Interior means it's inside the body. It's not a surface node, it's an interior node. Here's what it says in words. If you add the 4 temperatures of the surrounding nodes and subtract off 4 times the temperature of the center node, you should get 0. Now, that particular equation is in table 4.2. And that table has 5 different equations for 5 different kinds of nodes. I'll give you a for instance. Now, if I wanted to model this problem for finite difference analysis, I would first of all, I'd space the nodes out. I'm not going to do them all, I'll just do a few. So I better do some more, make it a little bit more practical. Okay, so there are the nodes. That's 1/4 of the whole picture. There. First of all, you set up your grid, the grid size. I don't know, delta x equal delta y equal 1 centimeter. Delta x equal delta y equal 1 millimeter. I don't know, whatever it is. Then you sketch it out. Then you say, okay, do I have any interior nodes? Oh, yes, I do. 1, 2, 3, 4, 5, 6. Got them. Do I have any nodes that lie on a plane surface? Surface, so don't forget, surface or interior. Do any nodes lie on a plane surface? Yeah. 1, 2, 3, 4. 1, 2, 3. Got it. Do I have any corner nodes? Oh, yeah. Corner nodes. Yep, he's a corner. He's called exterior corner. He's a corner called interior corner. So you have in this problem 4 kind of nodes. Interior nodes, number 1. Surface nodes, number 2. Exterior corner node, number 3. Interior corner node, number 4. 4 equations in table 4.2, 1 for each of those nodes. So, then you go ahead and write this equation for every node in that problem. I don't know if there's 40, 50 nodes there, whatever it might be. And then you solve them. You've got 40 equations with 40 unknowns. Okay, I don't care. TI 2050, you spend a lot of money for it, good, use it. Excel, yeah, use it, whatever. Whatever method you can do to solve those equations are fine. Okay, and then this problem here, there's other problems too. If there's convection, there's an equation in table 4.2 for convection. So if this is not given, but this is T infinity, and there's an H on that surface, there's an equation in table 4.2 for convection on a surface also. So there's a lot of information in table 4.2 to set the problem up correctly to solve for the temperatures at those various nodes. Once you get those temperatures, then you can get an estimate of how much heat flows from the hot surface to the cold surface. But step 1 is get the temperatures. Step 2, get the heat transfer. Okay, good stopping point. So reminder, homework due today. We'll see you then on Monday.